All right, you guys, so here's part two of the third ocean lecture. So we talked last time about those atmospheric circulation cells, and you notice they were really symmetrical about the equator. In reality, they're not always perfectly symmetrical about the equator. If you go on, everything that you've learned so far will totally help you, and you'll just learn some of the little changes that happen. Now, there are seasonal changes. I don't know if we'll get a chance to talk a little bit about the monsoon that happens in that northern part of the Indian Ocean. But boy, the circulation patterns change big time there from winter to summer. And it does have to do with the fact of heat capacity. We talked about heat capacity before. It's so important. The continents heat up so much faster than the ocean. And so in the northern hemisphere, where we have a lot more continent than ocean, things are going to be thrown off by that. So because of those uneven distribution. So there are a few changes. If you become an atmospheric scientist, you'll learn them. But these patterns that I've taught you will hold up. All right, quick review. Different amounts of sunlight are received at different latitudes, with the tropical and equatorial latitudes receiving the most. Let's see, why do we have seasons? You got to know that. It has to do with the Earth's tilt and which hemisphere is receiving more direct sunlight. You do need to know about the Earth's atmosphere. There, you got to know about the troposphere and the stratosphere, and what are the main gases in the troposphere, etc. Convection, we're not getting away from convection. It was in the first exam, the second exam, hey, it's on the third exam, and it's density driven. Air warms up, expands, rises, cools down, contracts, and falls. Okay, if I use the fact that it rains every day at the equator to really, put me where I need to be to learn all that other stuff and understand all of the relationships. So we have equatorial and subpolar lows. We have tropical and polar highs. Wind always blows from high to low, never the other way. And the Coriolis effect, the main part of that you got to know is that the offset is to the right in the northern hemisphere, to the left in the southern hemisphere. Remember to look down the shaft of the arrow. And why do we have the Coriolis effect? Because we got an Earth with a big fat belly. It's a sphere. And so the fat parts have to travel faster than the skinnier parts to end up in the same place 24 hours later. All right, you do need to know the wind belts and boundaries, and we're going to actually kind of mention them again in the next chapter or in the next section, because obviously if there's wind blowing across the surface of the ocean, it's going to create some currents, and we'll talk about that. All right, we got to talk about weather versus climate, and they're different. Weather is whatever's going on out there. Now, the weather people sometimes say, oh, we're 10 degrees less than normal, or we're 10 degrees warmer than normal. And kind of what normal is climate. Climate is weather data taken for at least 20 years, but probably for 50 years, and averaged. So you might say, well, why do people typically get married in June? Well, typically it's got nice weather in June, but you know what? It could have a snowstorm in June, and that's not the climate, but that's the weather. So weather's whatever is happening out there, and if you take data for 20 to 50 years and average it, that's climate. All right, storms. You know what a storm is. If I said, okay, pretend you're a storm, you'd be windy and rainy and thunder, lightning, and stuff like that. And why we have storms is because of air masses. Air masses are identifiable and mappable bodies of air that have uniform temperatures, humidities, and densities. And we'll talk about warm air masses and cold air masses. Now, storms are created when warm air masses and cold air masses meet, and there's actually two different ways that they can meet. And right now in the news, where you keep hearing about all these incredible tornadoes hitting central United States, because we're in the middle of tornado season, and that's because we have a front, and we're going to have a very specific type of a front, a cold front. Okay, and a front is the boundary between when a cold air mass and a warm air mass move. Now, which one is moving into the other's territory is kind of important in determining. A cold front is where cold air moves into an area already occupied by a warm air mass, and a warm front is where warm air moves into an area already occupied by cold air, and they do behave very differently. They'll both produce storms and wind and rain, but boy, cold fronts are the ones that produce that tornado alley stuff, and so we'll talk about that. All right, so warm front, where warm air moves into an area already occupied by cold air. Now, when that happens, remember cold air is drier and denser. And so the warm air, which is wetter and less dense, has no problem rising up, and it rises up. And remember, when warm air rises, it cools. And when warm air that has a lot of water vapor and it cools, that water vapor condenses and rains out. And so, yeah, we get rain, but it's going to be spread over a much larger area than my next front, okay, my cold front. So this is not the type that typically would create a really dangerous storm system. Okay, this is the type, cold fronts. Now, cold fronts happen in that Tornado Alley part of the United States when cold Canadian air masses move down into an area that has already been warmed up by those warm Gulf. Remember, the Gulf of Mexico is warm water. And so you'll have warm air masses sitting over the lower and central United States, and then will come this, freezing cold Arctic or Canadian air, and it's moving, so cold front is where it moves into an area already occupied by a warm air mass. Now look at this. This rain is concentrated in a much, like half the distance, so a lot more rain in a smaller amount of area. And that cold air just hits that warm air like a freight train. Kind of does look like a freight train, huh? The new Amtraks. And that warm air rises up and creates thunderheads. It creates shearing, which was what creates the tornado. So not a pretty picture when you see these. All right, I wonder why there's two of those. All right, so that's just a little bit more information. I told you about all of that. All right, let's talk about hurricanes. Now, hurricanes, typhoons, and cyclones are all the same thing. They just depend on, they're named depending on what ocean basin you find them in. All right, what causes hurricanes? Hurricanes are caused by warm surface waters in the ocean and a low pressure system. Now that water has to be a certain temperature. It has to be 80 degrees Fahrenheit. And so typically our hurricane season for the North Atlantic is in the summer months, so I'll show you guys that, because that surface water has to heat up enough. And so if the water is 78 degrees Fahrenheit, we won't create a hurricane. But once it reaches that magical 80 degrees Fahrenheit, then we could possibly have a hurricane. So what happens is, again, it's kind of complicated, going to try and make it easier for you. Remember, in low pressure is where warm air is rising. And where warm air is rising, it's typically very wet. And also what's kind of important, something we talked about was kind of that latent heat, or when water goes from water in the liquid form to water in the gaseous form, there you have a ton of potential energy stored in there. And so when that hurricane finally hits, that's when you release all that potential energy, or that energy that's been stored through that evaporation of water. So it's pretty important. Hurricanes are rotating air masses, and it's kind of funny. In the northern hemisphere, they rotate counterclockwise. In the southern hemisphere, clockwise. So if you just saw one, you could tell by how it's rotating which way. It's called anticyclonic rotation. And you kind of know what they are, heavy winds, lots of rain, and again, that's that energy being, kind of hitting the land, and that energy being released. Now, hurricanes do weaken when they go over cold water or when they hit land, but boy, can they pack a mighty wallop, a couple atomic bombs worth. So here is kind of a cool slide. Now, you guys, you're supposed to be watching An Inconvenient Truth. And what's really amazing is that year, 2005, I believe, we had our first South Atlantic hurricane. And look at, Brazil got hit, and they don't have one marked on here. So I need to take this into Photoshop and fix it up. And the reason you don't typically have one is you see that little teeny lens off of Africa, right underneath the equator of warm water. In the past, it hasn't been big enough to produce one, but nowadays, because of global warming and sea surface temperatures rising, it is. I believe they call them typhoons in the Japan. They call them cyclones when they're hitting India or Bangladesh. So they're the same thing. It just depends on which ocean basin you're in. And typically when our hurricane season is over, then hey, it's Australia's turn for a hurricane season. And in the last few years, they've also been hit by some pretty amazing hurricanes. All right, to be Classified as a hurricane, you must have sustained winds of 74 miles an hour, not just wind gusts. You guys have probably been in wind gusts of 74 miles an hour, but to have sustained winds, this is a whole nother ball game. And there's a 1 to 5 scale, with 1 being the least horrible, but it can still be pretty horrible, and then up to a 5. And yeah, we do have 5s. And with a 5, category 5 hurricane, it's got to have sustained winds of at least 155 miles an hour. So a lot of energy. Now, we have a hurricane season, but you know what? That same year that we had Katrina, 2005, we had hurricanes before and after our hurricane season. And this is because of that global warming and that ocean temperature staying hot longer and also being hot earlier. So kind of not a good thing. There is a direct correlation between global warming and this increased number and strength of hurricanes. All right, so is this northern or southern hemisphere? And remember, in the northern hemisphere, it goes counterclockwise. In the southern hemisphere, clockwise. This is northern. It's going counterclockwise. All right, here's just kind of a little bit of anatomy. The eye wall is where the winds are the strongest. You guys all know about the eye of the hurricane is where it's all calm, and that's because you've got air sinking. That's where the little high pressure zone is, and the rest is a big low pressure zone. And then when you go back out of the eye and back into one of the eye walls, you're back into some pretty nasty conditions. All right, hurricanes can be absolutely huge across, over 1,000 miles across. They're pretty tall. They can go up pretty high in the atmosphere. Space Shuttle regularly gets good pictures, and now the International Space Station, of these big storms, and some of them are huge. They actually travel pretty slowly, though, when they're traveling across the ocean, even though, they've got lots of energy and they're in warm water. This took, 10 days or so for it to hit the Florida region. So these are not a surprise. Obviously, the farther out they are, there's more chances, they could cover a lot larger area. But the closer they get, they have a pretty good warning system. And you got to just heed the warning. If you have children, get out of that area. Go visit grandma or something until it's safe, because these things pack a mighty wallop, and it's not a party to ride one of these out. Many people have been killed thinking that, oh, we'll just hang out and ride this thing out. Okay, don't do it. Get out of there with your kids. What kills the most people is not the strong winds, it's the storm surge. You guys have all seen a lot of videos of the tsunami after that Japan earthquake. That's what it's going to look like. A storm surge looks like that, because you've got this big zone of low pressure coming on shore. It's pushing a wall of water, and it can be up to 40 feet high, you guys. This is just like a bad tsunami. This is what kills people and destroys most of the property. So it's really, the winds are bad, and the winds can hurt you, but it's that wall of water, and it can go for miles inland. All right, especially, think about the areas that get hit. They're the Gulf Coast and the East Coast, and these are low-lying coasts. We're going to be talking about emergent coastlines in our next lecture, and we are on an emergent coastline, so we're on a coastline that has cliffs on the West Coast, and so we have big cliffs, and that would help us a lot, but we're not typically going to get a hurricane. They're pretty rare. But those low-lying coasts, boy, those storm surges can go onshore forever. And they're worse when you have a high tide or a big storm system coming in and just making them go much farther in. So most of the destruction, damage, and fatalities occurs because of this wall of water. Okay, so don't mess with a hurricane. Lots of great videos out there. And in fact, I'm going to try to remember to put a video up of a stupid kite surfer who thought, oh, yeah, a hurricane's coming on, I'm going to go kite surfing. And it picked him up and blew him into a building. Yeah, I don't even know if he lived. I know he was very badly injured. So, don't mess with this stuff. Mother Nature is going to win. All right, we're going to talk about the greenhouse effect. And you guys, the greenhouse effect is a good thing. Okay, it's the runaway greenhouse effect that's a bad thing. We need greenhouse gases in our atmosphere because they hold on to heat. And if we didn't have any greenhouse gases in our atmosphere, the Earth would be way too cold. It would be 33 degrees Celsius colder, meaning that all water would be frozen. We would not have life. We need liquid water. So we do need some of those gases. We would naturally have some of these gases in our atmosphere. The bad thing is that these gases are rising in concentration, and because of us, because of our behavior, because of industrialization and clear cutting and things like that, and burning fossil fuels. And so this is really bad. Now, what greenhouse gases do, you guys, you all know what a greenhouse, it may be a cold day and it's sunny and it's cold and you go in the greenhouse and it's cooking hot. In fact, your car on a cold day, if it's sunny, your car can be pretty hot. And that glass in the greenhouse and the glass in your car, it allows visible light to come through. And visible light is how the solar energy, most of the solar energy that comes to the Earth is in that form. Now, the Earth absorbs that and then it radiates out at a longer wavelength, the infrared. And infrared is kind of like those heat lamps at cheap burger places that cook 100 burgers and then stick them under the heat lamps. So that's the energy that the Earth puts out. Now, the greenhouse gases allow that visible light to pass right on through, but they grab on to the infrared. And the more greenhouse gases we have, the more of that infrared heat it can grab onto and reflect back down onto the Earth's surface, heating it up. So a little bit's good, but a lot is really, really bad. And yes, our global temperatures have been rising. And again, it's the scale. It's not the fact that, yeah, probably in the past we've been warmer. It's the fact that in 50 years, not 500 million years, we're seeing these changes. Okay, so again, solar radiation is in the form of visible light. Okay, Roy G. Biv, the colors of the rainbow, the electromagnetic spectrum. You guys know a little bit about that. It comes into the Earth. The Earth absorbs it, and it radiates out a different wavelength. It radiates out infrared. On a hot day in the summer, you can feel the black top in the parking lot radiating out heat. That's infrared. Now, the infrared does not pass through the glass. It gets caught by the greenhouse gases in our atmosphere and is reflected back down, heating up that area. Okay, so that's the greenhouse effect. You're going to be asked to kind of explain it. Now, yes, the majority of radiation coming out of the sun is in the visible light range. Check that out. There's the colors of the rainbow. But look at Earth. The majority of the radiation coming out of Earth is in the longer wavelength, the infrared wavelength. Okay, so that's what the greenhouse gases grab onto. All right, again, visible light comes in, infrared energy goes out and is caught by those greenhouse gases. And the more that's caught, the warmer the Earth's surface. And the more greenhouse gases we have, the warmer the Earth's surface. Now, what are greenhouse gases? Carbon dioxide is the number one. Methane, okay, cows burp and fart methane. It comes out of landfills. Actually there's a lot of frozen methane underneath the Earth's crust in the ocean. Nitrous oxide, laughing gas, kind of weird, but yeah, that comes out of your car too. That is a greenhouse gas. Ozone in the troposphere, a bad thing. That is a greenhouse gas, comes out of your car. Now, chlorofluorocarbons, the United States has we stopped using them and we regulate them, I guess I should say, but third world countries still use them, and they are also greenhouse gases. Right now we're concentrating on carbon dioxide, but I'm going to show you guys a slide that we got to concentrate on all these greenhouse gases. Now, this slide looks all complicated, and it's not necessarily. Carbon dioxide is the main greenhouse gas. We've got the highest concentration. It is increasing every year. But what this slide shows you is that far right-hand column. Every 1 molecule of methane that goes out into the atmosphere is the equivalent of 25 molecules of carbon dioxide. It can hold as much heat energy as 25 molecules of carbon dioxide. Well, laughing gas, okay, every molecule that goes out is 200 molecules of carbon dioxide, the equivalent of. And those CFCs are 12 and 15,000. So this is pretty serious. Let's say we get on the carbon dioxide wagon and we kind of fix our act, but we have these other gases going up. We're still going to have a problem. We've got to deal with all of them. But yeah, it's probably not a bad idea to start dealing with carbon dioxide because we can so easily. Kind of bad news, but I have hope, you guys, because I've seen the ozone problem being fixed, and so I do have hope. I'm hoping your generation is smart enough to fix this up. All right, so global warming, is it happening? Absolutely, positively, yes. I have absolutely no doubt in my mind. The data says that. We know that since we had the Industrial Revolution and we've been, urbanizing and burning fossil fuels, that not only has the concentration of carbon dioxide in the atmosphere risen, that global temperatures have risen. Again, you guys watch Inconvenient Truth, skip through the political stuff, but watch all the climatic data, and they show you how this data is collected, and it is so telling. It's not lying. I'm not making it up. Okay, so again, huge increases. And it's more the rate that it's happening, you guys, because remember when we started off with a picture like this, it was 5 billion years worth of history. This is what, 250 million, or 250, God, I can't even say 250, it's too short, years of history. So it's kind of scary. So here's the actual data points, and this is the concentration of carbon dioxide up, up, up. Okay, now here's the Earth's average temperature. And again, if this was your investments over time, I'd say you're doing pretty well. This is an increase, but unfortunately, this is global temperatures, and they're rising, and it's happening way too fast. Okay, again, more data. This is just for the 50-year period. And again, if this was your investments, you're doing a great job. So people would say, oh, no, see, it goes up and down and up and down. But again, there is a trend upwards. And this happening so fast is what concerns me. All right, what's going to happen? I actually went to a conference once where people that were paid by, it's called the Western Fuels Association, by the oil companies, would say, oh, global warming is a great thing. People will take less sick days. I mean, they were just making stuff up, and I was not very happy. Higher than normal temperatures would raise the sea surface temperatures, and that's going to affect the climate. Again, Inconvenient Truth talks very nicely about this. We'd have increased rain, increased drought in certain areas. We'd have longer hurricane seasons, stronger hurricanes. Now, that same guy who said, oh, less sick days, you guys, I travel in the tropics a lot, and I have to get shots and take pills, dengue fever, yellow fever, I have to take malaria pills. These are tropical diseases, and they would expand like crazy, and they are ugly diseases. If you've ever seen people suffering from these, they die, a lot of them. So this is not good. I think those sick days would not be going down. Longer and more intense heat waves. Again, Inconvenient Truth talks about this. Remember, people can move. Well, sort of. We're way overpopulated, so not really. But animals and plants can't migrate this fast, and they will go extinct, and they are going extinct. Okay, polar ice caps will melt, and it's more the ice on land. The ice on land that melts will raise sea surface levels, sea surface elevations, and this will cause flooding. More than 50% of the Earth's population lives at or near sea level, and so this would be very, very bad. Even a 10-foot raise in elevation would be catastrophic. The ocean has been a carbon sink. I keep telling you guys, it's been our best friend. It's done a lot for us. It actually can remove carbon dioxide in the water, but as the water gets warmer, less carbon dioxide is dissolved. And again, it's been our best friend, and we've been abusing it. And, our best friend is in bad shape and isn't going to be able to take it much longer. We talked a little bit about producing limestone, and again, you can produce inorganic or organic limestone with those little organisms that make their shell out of calcium carbonate and produce those rocks. That would be removing carbon dioxide from the atmosphere. There's lots of different ideas going around. If we could increase photosynthesis in the ocean, maybe we could pull more carbon dioxide out, because remember, part of photosynthesis is using carbon dioxide to make sugar. So I don't know. I'm hopeful, but we need to make a change, and then what we need to do is try to use science to clean up after ourselves. But we have to stop pumping carbon dioxide out into the atmosphere.